So now we are left to prove M3. M3 holds with probability at least 0.99. So what was M3? M3 is that if you consider all the surviving vertices, remaining vertices, and then consider the hypergraph induced by those vertices, then almost all vertices have the correct degree, where the correct degree is as the expectation. So now, in order to prove M3, let's see what actually we need. For given x and e, we want to consider the edges e containing x, and then assuming that x is surviving, e also survives as long as other edges f which intersect with e is also chosen or not. If this holds and f is in M prime, then e dies. Otherwise, e survives. And we want to measure how many e containing x actually survives. So survives means that e is in H prime. So we need to consider this. For given x, we consider the edges e, where how many f are intersecting with e. So we prove this claim first, which tells you roughly how many f are intersecting with e. So all but and most delta sub 0, 1 and vertices x satisfies the following two. First is that its degree is 1 plus minus delta 0 n. So which is actually one of the conditions given. So this is the condition H1 that at most, all vertices at most this many has the correct degree. So x has to be the one of the good vertices, and B is all but at most delta sub 0.1 d edges E containing x satisfy the following. The number of edges f which does not, so these edges does not contain x but intersect with E is as expected, k minus 1 times d with some error bound. So we have x, so almost all vertices are good. So we have E, and then if all k minus 1 other vertices are good, have a correct degree, then degree close to d, then this is the expected behavior, the expected number of f. But of course, not all of them are good. So there are some small number of bad vertices. So it could be not this, but we want to show that almost all edges E, this holds. So proof. So let's prove this claim. By H1, all but at most delta 0 n, which is smaller than half times delta sub 0, 1 n vertices satisfies A. So the number of vertices not satisfying A is smaller than this. And then we want to show that the number of vertices not satisfying B is also smaller than this. Then altogether, at most this many vertices does not satisfy one of them, and all but at most this many satisfy both of them. So recall that the bad vertices are the vertices with degree not 1 plus minus delta 0 d. And rest of them, but those are still have a degree at most k times d. So we know that there are at most delta 0 and bad vertices. So, and each bad vertices has degree at most kd. So there are at most delta 0 and k d edges containing bad vertices. So far, I mean, nothing special. Give me a moment. So what's this? All but at most, I mean, this many edges with x satisfy this. So that's what we want to show. So we first check that how many vertices actually are contained in many of these edges, which contains a bad vertex. So hence, the number of vertices contained in more than delta sub 0.1 d such edges. Here, such edges are edges containing a bad vertex. Is at most we have, this many edges, and each edge contains k vertices. And then, if the vertex is contained in more than this many edges, then another vertex also consumed this many from the above computation. So this is at most this many. Again, here this gives you some relation that the delta 0 is actually smaller than delta 0.1 square over 2k, but this relation is already encoded in this hierarchy. So we have at most this many vertices. But if x is in E and E does not contain any bad vertices, any bad vertex, then we know the maximum co-degree is bounded. Then the number of edges f not containing x that intersect with E is, so you have x, E, and other vertices, and the number of vertices containing each y1, y2, and yk minus 1 is 1 plus minus delta 0 d, because they are all not bad vertices, they are good vertices. And we have to also consider we have to subtract the number of edges which contain x as well as one of these. So and also we have to, some are double counted. So, these edges are counted by y1 and y2 as well. So we have to consider all those things. K minus 2 delta 0 plus minus k So these counted all those, double counted one. So, and so we might have to like subtract or add this much. And then this counts the number of edges containing x and one other. So this, is give upper bound and lower bound. And which is again 1 plus minus delta sub 0.1 times k minus 1 d. So this number is exactly this number. So if we consider x and E is containing x and it does not contain any bad vertex, then this holds. But what we have just shown is that the all but at most this many edges with this. So here we said that there are at most this many vertices which is contained in more than this many edges having a bad vertex. So as long as we forget this and then we take other x, then it's the most of the edges containing this does not contain any bad vertex and satisfy this condition. So if we choose such x, then this holds, because such x does not belong to, it only belongs to at most this many edges containing a bad vertex, and all rest of the edges which doesn't contain any bad vertex satisfy this. So again, the first one, there are this many exception, and second one, this many exception not satisfying A, and this many exception, this many exception not satisfying B. So in total, at most, everything except this many vertices satisfy the both condition. Now our goal is the following. So most of the vertices satisfying these two. So those not satisfying those two, we don't care, because now we want to show this M3, which actually there are small number of the vertices that we can actually forget. So for this many vertices, we don't care what's the degree. But the rest of them has a correct degree. So we only show that the vertices satisfying this A and B, they are likely to have the correct degree. So let X be a vertex satisfying A and B. And we call on HE good if it satisfies 4.1. Let's say this is 4.1. So now what we want to do, we want to first conditioning on X is in B prime. What's the probability that a good edge containing X actually stays in H prime is, so we have X and E, and we already assume that X is in B prime, so it survives. And then rest of the vertices has to stay there. For that, all the vertices F which contains them and does not containing X, because here this F, we already assume that X is surviving, so we already conditioned on that this is not in M prime, so we don't have to care. So we only care about the edges which intersect with E at somewhere other than X. So this probability is that all of them are not chosen. So those events are independent. So all of them are not chosen. And how many edges are there? Because of this 4.1, this is the number. 1 plus minus delta 0 times k minus 1 times d. So this is the probability that a good HE actually survives. And also, and most delta sub 0.1 n H's, which is not good, H's containing X, which is not good, can stay with probability between 0 and 1. Thus, we can actually compute the degree of X in H prime. Its expectation is so say the number of, let's try it this way. So there are this many. So the degree of X is 1 plus minus delta 0 d. So which counts all the H's containing X. And among those, at most this many, delta sub 0.1 d many, may be bad edges. So these are the number of good edges. And each one of them stays with the probability 1 minus p to the 1 plus minus delta sub 0.1 k minus 1 d. And there are at most this many bad edges which can stay with probability between 0 and 1. Then you can actually compute that this is this. Again here, because this number is more or less this with the error term, which is approximately e to the negative alpha k minus 1 plus some big O of 1 over d, so which is much small, which can be all observed into this term. And of course, this, in order to that, this, or, sums up into some term here, but which is much smaller than delta sub 0.2. Now what we have to do? We compute the expectation, so now it's time to compute the variance. So again, how do we compute the variance? We decompose it into the random variable. We partition it into the indicator random variable, for which it's easier to compute the variance, and we consider the covariance, for which E containing X, let IE be the indicator random variable, which is 1 if it survives and 0 otherwise. Then this, degree is actually a random variable, which is sum of this indicator random variable. So what's the variance of this summation? Which is again, bounded above by the variance of each one, plus variance, covariance of different one. The first one is bounded by the expectation, because for indicator random variable, we know that the this inequality holds, because this is just nothing but the 1 minus expectation times expectation. And this is smaller than or equal to 0, equal to 1. So this is an upper bound. Again, we have this plus covariance of I, IF. So EF containing X. And this can be actually partitioned into two. So if one of E and F are bad, then what's our assumption? X is contained in not many bad edges. How many bad edges does it belong to? Delta sub 0.1 d many bad edges containing X. So if one of them is bad, then it's either E or F. We choose two, and then we choose a bad edge, and we choose any edge. And this covariance is at most 1. So this actually constitutes an upper bound on this covariance where E and F are, at least one of them are bad. And if both of them are good, we have this term. Because now our goal is to show that this variance is much smaller than expectation square. So, I mean, this is small number times d square, so which is, I mean, little o of expectation square, because expectation is roughly some constant times d. So this term is okay. This term is also okay, and we want to just bound this as a small constant times the expectation square. So now we have to consider the covariance of these two indicator random variables when both of them are good. So for this, we need to just fix E, which is a good E, and we bound covariance of IE, IF, F good. So we have E. Then now we have X and F. Now let's just also consider let's just show that we want to just consider the case where E and F share only one vertex X. So other cases are there are at most this many edges F with intersecting at least 2 points, because if we take these two, then we consider all the number of edges containing this, then that's at most the maximum codegree, which is this. And again, X and this other one, there are k-1 times that we can take, and which provide an upper bound on the number of such edges. So that many edges with the intersection at most 2. So, and their contribution to the sum, this sum is at most k-1 delta 0 t, because each covariance is at most 1. So now we consider the other case where their intersection is only X. Then again, similarly as before, we want to consider all the edges here. They are all surviving, and each one of them happens with probability 1 minus p. So we multiply them together, then we actually get the probability that IE happen. That's same here. But what makes these two are correlated? So for here, we consider all the edges, and then we just consider the probability that all of them are not picked inside of M prime, and then we multiply them. Then that's the probability of IF is 1. In other words, expectation of IF. Similarly for IE. But they are not independent because there could be an edge which contains here and here. Vertex here and vertex here. This edge should not be picked in order to this happen and in order to this happen. So that actually is related to both events. So that makes the covariance not 0. So let's indicate the number of such edges. Let TEF be the number of edges of H that intersect both E and F while not containing X. Again, we want to avoid containing X because we already assumed that X survived. So any edge containing X is not picked as a M prime. That's our conditioning. Then how large is this? This is actually at most k minus 1 squared times delta 0 t. Because if you choose one here, and then count the number of edges containing both of them, then that's at most delta 0 t. There are k minus 1 choice, k minus 1 choice. So this constitutes a upper bound. For such E and F, what we have is the covariance of IE, IF is expectation of IE, IF minus expectation of IE times expectation of IF. Again, watch this. In order E and F are both surviving means that if you consider all the edges intersecting both of them, at least one of them survive, meaning that they are not picked. So this is 1 minus P plus all, say, Y inside of E, but not X. We add a degree. No, it's not that. Let me rewrite that. Number of edges intersecting with E minus X not containing X. It's too long. Let's just say okay. This is A, and then number of edges intersecting with F minus X not containing X is B. Then this is A plus B minus TEF, because TEF is counted twice in this sum. On the other hand, here expectation is 1 minus PA, 1 minus PB. Then, again, this is 1 minus P, A plus B, 1 minus P minus TEF minus 1. So this part is at most 1, so we get an inequality if we just delete that part. And again, what do we know? We have this. So this is 1 minus alpha over D, and most minus K minus 1 squared delta 0 D minus 1, which is smaller than. delta sub 0.1. Again, so this gives us some relationship between delta 0 and delta sub 0.1. It's k minus 1 square delta 0 alpha some relationship along this line is enough to get this inequality, but this is already taken care of in the previous hierarchy of the constant. So this is at most delta sub 0.1. So now we can actually compute the summation of covariance. EF good, X, EF. Summation of all E, how much we add. For each E, we have this many edges, which contributing at most that, which is k minus 1 delta 0 D plus how much is here? So k minus 1 delta 0 D plus 1 plus delta D times delta sub 0.1. Each is this, and then how many F are we considering? The number of edges F containing X is at most this much. 1 plus delta 0 times D. So altogether, it's a number of edges times D. And then how many number of edges are there? HE containing X is again 1 plus delta 0 times D at most. So let's just say this is delta sub 0.3 times D squared. So now we can conclude that hence, if we condition on X is already in V prime, we have that the variation of degree of X in H prime is as before, the sum of expectation plus this part plus this part all together. Let's just say this was this over 2 even. So it's depending on the relationship between these two, so we can actually assume this over 2. And here this part is also smaller than that. So together here we get the delta sub 0.3 times D squared, which altogether, is more than, say, expectation squared times some small constant, say delta sub 0.4. So by Chebyshev again, the degree of X is 1 plus minus delta sub 0.5, say, times D times e to the minus alpha k minus 1. So which is, remember that the expectation was, where is it? This number. So it's not so, sorry, there should be negative here. Yeah, not so deviate from here. This, the probability that it does not hold with probability, say, and most small number. You can actually make it even smaller, but this is enough. So by using Markov, so we consider the number of vertices. Say X is the number of vertices which satisfy this. Then Then what we can show with probability at least 0.99 for all but at most 100 delta times 0.5 n vertices x satisfying both A and B satisfies this. So with probability 0.99, at most this many vertices plus the bad vertices at the begin with, which was the not the bad vertices, the vertices not satisfying A or B by this claim. So this many vertices and together with this many vertices might not satisfy the condition in M1. So as at most delta sub 0.1 and vertices not satisfy A or B, and this together is more than delta 1 times n. This proves that M3 holds with probability at least 0.99. So this proves the lemma. So it shows that M1, M2, M3, each of them holds with probability at least 0.99. So there is positive probability that all three hold, which implies that there exists a choice of set of edges M prime which satisfy these three conditions. So which proves the Rödl Nibble. Which proves the Pippinger theorem. And again, this, each time you nibbled it out some vertices, and then your hypergraph gets smaller and smaller. So that's why it's called the Rödl Nibble. This kind of method is called Rödl Nibble.